Hello class. The goal of this lecturette is to start the semester by reviewing what we know about the conservation of energy from our dynamics class, which you probably took just last semester. Once we review that, hopefully that'll provide a good base for us to discover the other aspects of energy that we're missing that we can learn through thermodynamics and incorporate into that knowledge of what energy is and how it's conserved and transferred. Let's take a few minutes to do just that. So let's review a few basics about energy, which we probably learned and picked up in high school, classes like physics and chemistry. First off, we know that energy is always conserved. It's constant, neither created nor destroyed. It's just something that's moved around in one form to another. Another basic idea is that energy can be thought of as the capacity to perform work, useful work. And we'll learn a lot more about work in the next upcoming days and classes. And third, energy has many forms as we conserve it, as we move it around from one form to another. And just a few examples that are useful to mechanical engineers would include chemical energy, energy stored in bonds between atoms, electrical energy, nuclear energy, energy released by splitting apart the atom, or even in the area of fusion energy research, bonding subatomic particles together. Mechanical energy, such as energy stored in a spring or gravitational potential energy. And another example would be thermal energy, which could be the form of radiation heat transfer, convection heat transfer, conduction heat transfer. So then, last semester, most likely, you took ME or CEE 2123, which was a course about dynamics, specifically rigid body dynamics. And in part of that course, we learned to view Newton's second law through conservation of mechanical energy. We could rewrite it or re-derivate F equals ma into a form of energy that's conserved. And for conservative forces, we learned in rigid body dynamics, the energy in the system is constant. So what that does for us, mathematically we can say that E1 equals E2. And the subscript was my indication for some position in space. So I defined some sort of system, and it could have one position in space, and then it could go through a process and end up in a second position in space. And I would say that at each of those two states, the energy in the system was constant. It was conserved. And again, using the terminology from that dynamics course, we broke the energy into two components, which we called T and V. V we thought of as potential energy, and T we thought of as kinetic energy. And now both of those had different possible components as well. So for potential energy, we learned of two main components in terms of mechanical energy. One would be gravity, gravitational potential energy, and we would have written that as the weight, mass times gravity, times the height from some sort of datum. Another form of mechanical potential energy would be that stored in a mechanical spring. And we saw that that took the form of 1/2 K, which we called a spring constant for the perfectly elastic spring, multiplied by the displacement from the unstretched state squared. And in terms of kinetic energies, we saw in the dynamics course two components. Since it's a rigid body, that body could translate, and that would take the form of 1/2 mass times the speed squared. The body, since it's a rigid body, could also rotate about some point of rotation. And we saw with that rotation, kinetic energy being equal to 1/2 the mass moment of inertia times the angular velocity squared. So this was our world in terms of conservation of energy for rigid body dynamics. So by reviewing what we learned about conservation of energy in dynamics, we can now step off from that base and expand our knowledge, make it much broader in scope by considering the wider world through thermodynamics. Let's start by looking at some of the assumptions from dynamics that were implicit in everything we did in that course. First of all, we worked with rigid bodies only. Well, what happens if the object is not rigid? What happens if the object is not a solid at all, but a fluid? For instance, a thermodynamic power plant that creates electricity commonly uses the Rankine cycle, where water is the working fluid. And that water moves as it flows from one component to the other, and it even changes phases as it's vaporized and condensed. We have no way of handling that in our current dynamics state of knowledge. Also, we limited ourselves to mechanical energy only. What about those other forms of energy that were mentioned at the beginning, especially thermal? And also, we limited ourselves to conservative forces in dynamics. Well, what about friction? Friction is the big thing that robs us of useful mechanical energy by heat conversion to thermal energy, heat transfer. So there's another connection to the thermal side of things. And that's whether you have two solids in contact with each other, rubbing against each other, or we looked at projectile motion, for instance, and we always assumed that friction was negligible. Air resistance didn't matter. Well, we need to expand our knowledge of energy conservation, and that's what thermodynamics is going to do for us. So if I take my conservation of mechanical energy statement from dynamics, what I need to do is come up with new models to handle these limitations. And so I'll just put some big question marks right here. We're trying to add these new ideas into this idea of conservation of energy. Let me rewrite this just a little bit more here, and that'll put us in a good place as we read into the next sections in the textbook. I'll just regroup things. Okay, and this finally gets me into a form that we'll see as we read more about conservation of energy, the first law of thermodynamics. We'll call the change in kinetic energy delta KE, so we're now matching the terminology in our thermodynamics textbook, and the change in potential energy going from one state to another is delta PE. So then this becomes our placeholder for what we're going to learn about things such as the work of a fluid, for one, thermal energy, for another, and I'll just write other energy terms as well. And that's where we're headed.